Hey guys, how's it going? Welcome back to day 27, getting ready for Monday. Nice work today tackling that test. Today we're looking at differentiability and critical points. So let's start with differentiability. Differentiability means that we can, right, if we think about the root word there, differentiate, right, refers to derivatives, right? So if something is differentiable, that means we can take the derivative of it. So let's talk about a function being differentiable. If I tell you that a function is differentiable everywhere, that means we can take the derivative at any x value, at any x value. Okay, so if something has a point that is not differentiable, that means we can't take a derivative there. Okay, so this is like it's similar to continuity, but it's a little bit stricter of a definition. So let's just take a look. It's easiest to kind of see this through graphs. So let's take a look. When we look at a graph of a differentiable function, we're going to notice two things. We're going to notice that the graph is continuous, but it's also, I like to call it smooth. So here's a function f of x. And this graph appears to be differentiable because not only is it continuous, right? We don't have any jumps, holes, asymptotes, anything like that. But also notice how it's smooth, right? So smooth and connected. That's how I like to describe myself too. I'm pretty smooth and connected. But all jokes aside, when we take a look at this graph, right, we could find the derivative anywhere because we can find a slope of a tangent line anywhere, right? Pick any point on this graph and you can find, right, a slope of a tangent line at any of these points. Now, polynomials, right? Quadratic, cubic, quartic functions are all differentiable. Linear functions are all differentiable, right? Because we can do the derivative and evaluate it anywhere, okay? But what we're going to look at now are some things that cause problems to differentiability, okay? One of those things is called a corner. One type of function where we see corners come up are on absolute value functions. So an example would be this function here. Let's think about graphing that function. What would it look like? Well, it's your absolute value function shifted right 3 and up 2. And we know that our absolute value functions look like these, right? It would look something like this. Okay. Now, we can take a derivative anywhere here except for at one point. The corner causes a problem. Okay. So we have our corner right here, and if you think about trying to do a tangent line there, there's lots of different lines that could go through that point and that point only, right? If we notice, the slope is different just to the left of the point than it is to the right of the point. Okay, it makes a drastic change like that. So this graph would be differentiable everywhere except at x equals 3. By the way, diffable is what I use for just to shorten up differentiable. It's such a long word. F is not diffable at x equals 3. Okay? I can't put a tangent line in there because there's a lot of different ways that I could draw it. So anytime we see a corner on a graph, okay, that's showing that graph is not differentiable there. Now, was that graph, now that I marked it all up, okay, but was that graph continuous? Well, continuous means I can draw it without picking up my pencil. Yes, I can. Okay, so it was a continuous graph. There weren't any holes, jumps, or asymptotes, but it was not differentiable. Okay, so it fails differentiability, but it still passes continuity. Okay, let's take a look at another type of thing we can see as a cusp. Cusps also cause differentiability problems. They look kind of like a corner, but they're a little more curved coming in. So here's an example of a cusp. Anytime we have a cusp on a graph, we're going to have differentiability problems at that point. Because for the same reason as the corner, right, I can't match a tangent line right there, right? The slope changes too drastically at that point. So cusps cause differentiability. So this graph would be not differentiable at whatever x value that is. So corners and cusps are common problems to our differentiability. Okay, the third thing we have that we can have that's going to cause us to fail at differentiability, right, to make something not differentiable, is vertical tangents. We see vertical tangents on a lot of different functions. One of the most common is rational exponents, like x to the 1/3 has a vertical tangent on it. Okay, what a vertical tangent looks like is this. So there might be a point right here where the tangent line is vertical. Okay, if the tangent line is vertical, that means the slope of the tangent line is undefined, because we know vertical lines have undefined slopes. Think of it like a terrace point, but on its side. Okay, they look like terrace points, but they're on their side. Okay, those are vertical tangents, and vertical tangents cause differentiability problems, right? Because again, a derivative is the slope of the tangent line, and if the slope of the tangent line is undefined, that means we can't do the derivative, therefore it's not differentiable. Okay. Also, if you think about like a circle A circle would have points that have vertical tangents. If I draw a circle, this point out here on the edge, right, the slope of this tangent line here, right, it has a tangent line, but the slope is undefined because it's a vertical tangent. So anytime we have vertical tangents, we have differentiability failures. And the fourth thing is any kind of discontinuity breaks differentiability. So again, whether it's, you know, a hole or a jump, or you know, I should. So any kind of discontinuity that we have automatically means the function's not differentiable there. Okay, which brings us to a very important part. Okay, if we know a function is differentiable, that guarantees that the function is also continuous. The way that this is often said in the math world is differentiability implies continuity. So if I tell you that f of x is differentiable, you know that f of x also has to be continuous, which is a really important point. So let's go ahead and put that in our notes here. Okay, so this is where it gets interesting. Okay, so if a function is differentiable, it guarantees the function is continuous. That's implied. But if you need to show that something is continuous, right, and all they say is it's differentiable, and you're doing a justification, like for example on the IVT, right? If they say f of x is differentiable, and then they ask you an IVT question, you need to, in your justification, say that since f is differentiable, f is continuous. You're going to need to make that statement. Because IVT requires continuity, they need to know that you know that differentiability implies continuity. So if I tell you f of x is differentiable, therefore f of x is continuous. It guarantees it. But it doesn't work the other way around. Okay? For an example here, let's think of differentiable like golden retriever and continuous like a dog. Okay? If I tell you that I have a golden retriever, then you know that I have a dog. But if I tell you I have a dog, that doesn't guarantee that I have a golden retriever. Okay? So that's how this relationship works. If you know f is differentiable, you get for free that f is continuous. You're just going to need to state that. Okay, but if I tell you f is continuous, you can't assume f is differentiable. Okay, it doesn't work that way. Okay, the last thing, just a quick definition here, is for critical points. Critical points are very, very, very important, and we're going to use them a lot in this next unit. So here's what a critical point is. So f has a critical point when f prime of x equals 0 or f prime of x is undefined. Okay. That's the definition we have to have. This is very important. I'm going to ask about that a lot, okay, and I need you to not only write that definition down in your notes right now, but commit it to memory, okay? So if I give you a function f of x and I want to find and I ask you to find the x values of the critical points, right, all we have to do is take the derivative and set it equal to 0, or take the derivative and figure out where that derivative is undefined, okay? Now this ties in nicely to differentiability because we just talked about f prime of x being undefined, places we can't find the derivative. So let's take a look at a graph here. This is a graph of f. We were looking at this graph and trying to determine where critical points might be. We're looking for f prime of x to be equal to 0 or f prime of x to be undefined. Well, when we take a look at this, I see f prime of x being undefined right here because that's a cusp. I see this point right here, f prime of x equaling 0. Because again, what that means is the slope of the tangent line is 0. Are there any other places where the slope of the tangent line looks like it would be 0? Well, at this little top of the hill here. And on this terrace point right in here, it looks like there's a point where f prime of x equals 0. What we're going to push this towards is critical points are going to be places where we might have a maximum or a minimum, like a local maximum or a local minimum, or it could be like the one farthest on the right, could be neither a max nor a min. Okay, so critical points are going to be very, very useful for us in this next unit. I just wanted to get you a little jump start on what they are. All right, that's it for today. I'll see you guys on Monday. Talk to you later. 2 chains, bye.